we have progressed from being able to withstand only a small range of environments to spreading our presence to practically every region of the Earth, and now beyond it, as the limitations of our intellect, materials science, and chemistry have risen. Even in the most hostile environment we have yet encountered, the vacuum of space, humans have existed continuously for more than 20 years. Why not Mars then? It must just be a matter of logistics if humanity can survive in Antarctica and space, respectively. Maybe humanity can survive and perhaps flourish on the surface of the red planet if we can get enough resources there. However, that if is working quite hard. The astronauts had to transport all they needed for their trip to the moon in their little frail landers. The Apollo missions only spent 1 to 3 days on the moon's surface, and they arrived there in under 3 days. Spending only a few days on the planet won't be enough for an astronaut headed for Mars, who will spend months in orbit just getting there. Every mission, even the first one, must be prepared to last many months, which greatly increases the logistics complexity. Landing on Mars is very challenging, because it is too far away from Earth for any descent to be controlled remotely. An average radio signal travels that distance in 12 minutes. Everything must be pre-programmed. There have been numerous new and costly craters created by a single mistake in the computer or its inputs. The period of time between the landing order and a successful landing is referred to as the 7 minutes of terror. Once the landing order has been given, no one in mission control can do anything to stop it. The shaky Martian atmosphere makes landing more difficult. Even the newest generation of enormous, supersonic-rated parachutes struggles to offer considerable traction on the tenuous air on the way down because it is so thick that any orbiting spacecraft needs a heat shield to keep it from burning up. Otherwise, our landers will crash on the icy Martian surface and lose all remaining orbital velocity. Various techniques have been employed, but the Sky Crane, a disposable frame loaded with retro rockets that fire until it is floating a few yards above the surface, has proven to be the most consistently effective. Then, before its fuel runs out, it gently pulls the lander down, releases its connection lines, and flies a safe distance away. These computations are really well judged, as predicted. For every pound of the lander's components, batteries, solar panels, and scientific experiments, the Sky Crane requires several kilograms of fuel. Additionally, the rocket that launches the Sky Crane into Mars orbit needs many additional kilograms of fuel for every kilogram of fuel in the Sky Crane. If we could, we'd send bigger, better landers to Mars. But we can only send subcompact-sized rovers there due to the limitations of rocketry. This has significant ramifications for carrying out a crewed trip to Mars successfully. We must accept that this scenario is impractical, despite our fantasies of a massive silver rocket gently descending to the dusty red surface with all the astronauts need for their lengthy stay. We won't be able to launch that rocket, and the far bigger spacecraft needed to transport it for decades, if not centuries. We must work harder and take advantage of every opportunity if we hope to plan a successful Mars mission and establish a permanent presence on Mars. This covers the kinds of animals we can discover on Mars. Both distinct threats and abundant riches can be found on the planet Mars. On the positive side, we may avoid bringing water if we choose our landing place wisely. There is nothing we can do to make water lighter. It is already quite heavy. There is nothing we can do to make it smaller. Thus, it takes up space. The astronauts will still need a certain quantity of extra water, even with the finest recycling facilities. However, there are numerous locations on Mars where water, in the form of ice, is simply a component of the soil. When you use a shovel, water ice makes up half of what you remove from the ground. Additionally, we may use that water for a variety of purposes outside drinking. it may be electrolyzed into its constituent gases. We don't need to take tanked air, since we can breathe the oxygen. Additionally, if we combine it once more with hydrogen, we have an explosive combination that might be used as a basic rocket fuel. If we take it a step further, we can synthesize hydrocarbons for a better burn by recovering carbon from Mars' atmosphere of carbon dioxide. Additionally essential for plant growth is that carbon dioxide. Supplementing our freeze-dried meal packets suddenly becomes not just an option, but also a mission goal when water and a growth medium are added. Although we eat a lot of calories as humans, we also feast with our eyes. A side salad is not only nourishing, but also uplifting. Then there is the actual Martian material. That can be used as building material. We can use it to produce bricks, or just pile it on top of our current constructions. And since life isn't easy on the Martian surface, we really need to do that. The temperature comes to mind first. Mars' atmosphere is too thin to tame dramatic daily changes due to its average distance from the sun of 80 million kilometers, 50 million miles. High summer temperatures can soar to a comfortable 21 decks, 70 dec. Yet that same day, just before dawn, we'll have seen readings of 90 dec, 130 dev. Temperatures can drop so low that they completely freeze the atmosphere's carbon dioxide. The extra insulation provided by several feet of Martian soil is going to be a welcome bonus. Additionally, radiation, a long-term concern, will be lessened. The sun constantly emits high-energy light in the form of gamma and X-rays, as well as charged particles. We are shielded from the solar winds surrounding us on Earth, and to a lesser extent on the Moon, thanks to the planet's strong magnetic field, which reaches into space. Even though the conditions on Mars' surface aren't immediately life-threatening, the lack of a magnetic field causes astronauts to accumulate radiation damage 10 to 20 times faster than they would on Earth. This is without taking into account the occasional solar flare, which can pack a decade's worth of exposure into a single event. One reasonably simple solution to this radiation issue would be to bury the astronauts' base beneath the surface of the Earth. Building it within a cave is another option. On Mars' volcanic regions, lava tubes have formed into enormous caverns that may be accessed through partial ceiling collapses. The soil itself is hazardous and perchlorate rich. Perchlorates are water-soluble. Therefore, even though they may be an oxygen source, contaminated soil cannot be used as a growth medium. The dust comes next. Due to the continual grinding of volcanic ash over hundreds of millions of years, the red dust has become so fine that even the feeble Martian winds can lift and maintain it for weeks at a time in the air. The dust has transformed into a nanoparticle with an average size of 3 1/10,000th of an inch, which poses a serious risk to both us and our machinery. Even with assiduous procedures like cleaning, vacuuming, anti-static screens, and air filtering, it would be very difficult to completely remove the dust from living areas since astronauts would bring it in from outside outings. As a result, it would end up in their food and air they breathed. Along with the previously described perchlorates, fine-grained rock powder can harm the lungs and eyes in addition to other cancer-causing substances. One rover has already been lost because to the dust coating its solar panels. We must be more confident in our seals and surfaces the more complicated the technology we use. Strict adherence to the maintenance schedule would be required, as well as extra components to support it. So how would we go about doing this? The amount of crew members we deploy, the length of their first stay, and their intended course of action all serve as guidelines for us. If we're planning anything more than a one-time visit, we need to keep an eye on the long game. What type of infrastructure can we develop that will be beneficial in the future? We must prepare to provide them with housing, water, and food before bringing them home. The most practical approach is by far to divide the problem into smaller, more manageable chunks. We may utilize the knowledge we get from such incremental efforts and what we have previously learned to direct our progress through the numerous components required to carry out a successful and long-lasting Mars mission. We would need to improve our capabilities in low Earth orbit as the initial step. The biggest spacecraft we've ever created will be needed for a multi-month mission to Mars, and it very probably won't be able to be lofted in a single launch. It will need to be built in orbit using techniques similar to those used to build the International Orbit Station. Fuel will need to be transported from Earth twice, as it will be returning, along with everything else required to sustain life throughout the lengthy voyage. Separate from the main body of the spacecraft, the descending craft will remain in Mars orbit. Sending supplies in advance to the planned landing place would be the second step. Sending robotic, self-erecting modules is a good idea if we can. This would allow us to prioritize a safe landing without adding more weight to the descent phase from food, fuel, oxygen, and water. It would also guarantee that there would be a safe place for the newly arriving astronauts to go. Additionally, by doing it this way, we would be able to delay sending people to Mars until we are certain that there is adequate support infrastructure in place. We would simply fire another rocket if one went awry. More than one is statistically likely to be lost. An ascent module, an empty spacecraft that can land on Mars and then refuel from the Martian atmosphere in preparation for a trip back to the transfer ship in orbit, would be one of the pieces of equipment we'd send ahead. To be clear, nothing in this is without danger. Before Apollo 11's landing, a famous alternative speech was given to U.S. President Richard Nixon in 1969 that addressed the possibility of disaster. There are still some circumstances that would be nearly hard to recover from, despite the fact that our meticulous planning has increased the likelihood of success. How long it would take us to respond to the unexpected is the fundamental reason behind this. One of the most undervalued and misunderstood components of a contemporary economy are supply networks. We are accustomed to placing orders from everywhere and having them delivered in a couple of days, if not hours. Retailers guarantee delivery that is practically instantaneous, while manufacturers maintain just-in-time inventories from their suppliers. A marvelously intricate network of staff, transportation, inventory management, and communications is hidden behind those stores. Only when it fails do we notice it. The entire planet is interconnected. Important pharmaceuticals, microchips, engine components, and even live organs for donation are effortlessly transported across borders and continents. This isn't always the case, though, and those instances provide us with our first glimpse at the difficulties that a Martian colonist may encounter. Now picture any issue taking place on Mars. Earth to Mars will take 9 months, if the launch window is kind. There will undoubtedly be a reduction in that as space drives advance, but the immense distances between the two worlds cannot be eliminated. 56 million kilometers, or around 35 million miles at best. The distance between Earth and Mars, at their farthest points, is 400 million kilometers, see 250 million miles. It would undoubtedly be the longest supply chain in history, with the most hostile environment we have ever experienced at its end. From England to Australia, the trip took less time even during the age of sail. If you were the first Mars mission's doctor, you would have to choose what medications, bandages, and surgical tools you wouldn't be taking instead. What is not necessary? There are limits to both weight and space. How will you decide between this vital spare component and that crucial spare part if you're the engineer? Naturally, you may request that the mission planners send 1 or 2 of each item. But how realistic is it considering everything that has come before? There will come a day when enough is enough. It is necessary to accept the possibility of dying via sickness, asphyxiation, accident, illness, or famine. The hardest work will be assigned to the early settlers, as it is with all pioneers. They'll be in the most risky, vulnerable, and unpleasant situations. Those who come after will have it easier, if not necessarily simpler. As long as Earth supports the endeavor, the original base's infrastructure is built to be enlarged, because it is a given that Mars will be completely dependent on Earth for many years. But how would a Mars colony develop into an independent nation? Can we really see that far out? Manufacturing is an important technique in this context, since it produces both the chemicals necessary for life and the common but essential supply of spare components. A certain level of security for colonists will be provided by specially formulated medications, nutritional supplements, and plant nutrients. 3D printers with a huge library of models will start to deal with the physical, and automated synthesis machines can create the biological components. The colonists themselves, and particularly their education, would be another pillar of a more autonomous Mars. Though need is sometimes the seed of ingenuity, Mars would be a very strict teacher. Learning would take up a large percentage of a Martian colonist's time. A functional colony would require a high degree of technology, and the number of people could only be as many as there was food and oxygen for them to breathe. Everyone is an expert in 2 or 3 different fields of expertise. Therefore, an unfortunate event to one need not cause a problem for everyone. New social mores and behavior norms will undoubtedly arise as a result of how fragile life is there. Martians will be heavily depending on one another for their very existence, not hardy individualists, and their relationships and laws will reflect this. It remains to be seen how far colonists deviate from the homeworld. However, a free Mars wouldn't be a carbon replica of any civilization on Earth. It would be deeply and breathtakingly strange.